the log of the denominator has no beta dependence, so we can forget about that. The log then of the numerator, the log of the exponential here is just, so log q to the n is just n log q, right? So this becomes times the logarithm of that Oh, this is reflected. Sorry, we need that's what I wanted to say. Times the partial of that with respect to beta. Q. Right? I started off, there's not a beta here. You guys nodded your heads. You shouldn't say that. I knew something was bothering me. That's it, there's no beta there. You can go back and look for it, it's pretty obvious. Okay, so this is what you get. Or, I give it this way, n times the sum of, well, that's fine. Yeah. So what I'm getting at is, for Boltzmann statistics, this is a probability, right? This is the energy of a particular single molecule state, and this is the probability of that state, right? Or the average probability of that particular state. So this is a probability of state J. Yeah, it's probability. So let's call that. Before we used capital P for probability, that's for a system. The book introduces the Greek notation pi for the probability for a particular single molecule state. Okay. So cool. And then if you multiply that by epsilon, take the sum, that gives you the average energy. That's Boltzmann statistics. What I want to do then is show you that either Fermi-Dirac statistics or Bose-Einstein statistics in the limit of large temperature, high temperature, goes over to the same probabilities for the distribution of single particles among the different states. And if the distributions of the particles among the states are the same, then all your properties are going to be the same. The book does it for both fermions and bosons. I'm just going to do it for Fermi-Dirac statistics so you get the idea. And then I think that's all that we need to do in class. So in general, an expression for now we do have the 1 over beta. So remember, we're in a grand canonical ensemble. The number of particles in a particular system is not fixed. Mu is fixed, but the number of particles is not. And we saw that the number of particles can fluctuate. You know, we saw the signs of the fluctuation. It's probably small. It gets smaller and smaller as the system gets bigger and bigger. And the average number of particles can be obtained from the grand canonical partition function this way. Okay. So I want to do a little math. I want to convert from, well, I really want to convert from between lambda and mu. So remember that lambda is exponential of beta mu, right? So the partial of lambda with respect to mu is so this becomes, the beta cancels the 1 over beta. Okay. So that's what we need. This is not working. And we want to use for arc C, the grand canonical partition function, this one right here. Right, that's, so we want the partial with respect to lambda, and that's partial of log this with respect to lambda. So this will be let me move this lambda from here all the way up to the numerator. It goes to easier. And the partial of this with respect to lambda is just that. And we need to sum over all of the i's. You with me? Okay. So that's cool. Now, just as up here, we identified this as the probability of state J. Remember that in average is going to be the sum over the average populations of the individual states. That's like a constraint. So we can identify that particular ratio as the average number of molecules or particles in state I. Okay. So this is in some way analogous to this. And if you wanted to form the pi sub I, and this are obviously different. They're not the same thing. So we can see that Boltzmann statistics and Fermi-Dirac statistics give different expressions for the population for the probability, different expressions for the probability of finding a particle in state I. So they're different. Now what about the limit of high temperature though? Thus far I haven't talked about temperature. This is true for any temperature. Fermi-Dirac statistics, this is Boltzmann statistics up here. Well, let's think about Fermi-Dirac statistics in the limit of high temperature. Because things will simplify. In the limit of high temperature, and let's think about n sub I. Yeah. As temperature gets higher and higher, the number of available states becomes greater and greater, right? And as the number of states becomes greater and greater, the average population of any state becomes smaller and smaller. When you get high enough, the average population starts tending towards zero. I won't say it becomes zero, but it goes towards zero. And lambda gets also very small. There are a couple of different ways to see this. You have to think about what lambda represents. It represents an activity. And as the temperature becomes very, very high, the activity goes to zero. So if lambda is getting small, then in the denominator, we can ignore lambda times the exponential and only the one is important. So as temperature becomes large, solving for lambda, I want to manipulate this a little bit. First, I'm going to sum over all the i's. Of course, the sum over all the i's, n sub i's, is just n average. So that lambda and if I substitute this back in for lambda, I can see that so the average population of state I is equal to the total number of particles in the average number in any particular system times this factor. So this is a probability. That's our pi sub I. And this is the same as this. So notice that phi sub I for Fermi-Dirac statistics is the same thing as pi sub I for Boltzmann statistics. So, if the populations of the states are the same in both cases, then all the properties are going to be the same. All the thermodynamic properties will be the same as well. So, is that clear? This right here is the take-home. So what I've shown, the two take-home messages thus far are this one, the expression for the grand canonical partition function in the case of Fermi-Dirac, or Bose-Einstein statistics is this, and over here, in the limit of high temp, the populations of the individual states are the same for Fermi-Dirac statistics as for Boltzmann statistics. Okay. Those are the two important consequences. Now, I said as T approaches infinity, how high do you have to actually be in terms of temperature? For most substances, really, by the time you get to 100 Kelvin, you're okay. For most purposes. Really, really exact purposes, maybe you have to be more careful. But for the kind of accuracy that we usually need, for everything except hydrogen, helium, and maybe argon in some cases, you'll be fine. Certainly at room temperature, you'll be fine using Boltzmann statistics. So for the rest of, really for the rest of the course, we're going to use Boltzmann statistics. But I want you to remember that if you get really cold or really light, you might have to use the Bose-Einstein or the Fermi-Dirac expression for the partition function. But that's no problem. I mean, it's simply written down in terms of energy levels and the lambdas, which come from chemical potentials, numbers of particles. So there's nothing mysterious about this. It just looks a little different. You won't use it as often, so it'll seem mysterious. But in principle, it's fine. Now, everything we've said has assumed that there's no forces between the particles. If there are forces between the particles, everything changes. So we've now really laid out all of the groundwork for thinking about systems of non-interacting particles. And we're now going to apply this methodology or this approach to some simple systems. We're talking really about perfect gases, ideal gases. And the book has a little short chapter for the simplest case, the monatomic gas, and then the second diatomics, and then polyatomics. So we'll can read through them pretty quickly, but it's very good to take it one at a time. And in the case of the monatomic gas, all you have to worry about is translation. Diatomic, rotation and vibration, and polyatomic, the same thing, but there are more vibrational states, and you may have anisotropic rotation, so you have to think about more things. So that's how the next couple weeks will proceed. Of course, we don't want to stick, if we can help it, to only perfect gases. We want to see how can we extend our approach to real systems. So our first step beyond perfect gases will stay with gases, but we'll introduce interactions, but assume the interactions are small. And that will allow us to use one approach, sort of Taylor series or gradual complication. Then if we have time, and I think we will, we'll begin to approach condensed phases where the interactions are much stronger. So in the case of real gases, you can think of the interactions as perturbations on the ideal case. When you get to condensed phases, you can't any longer just think in terms of perturbations. You need a new methodology altogether. So that's how we'll proceed. Maybe I'll finish by quoting from the book. This was our expression for the grand canonical partition function for Fermi-Dirac or Bose-Einstein statistics, and what I said cavalierly was, if you got the grand canonical partition function, then you can calculate any bulk property you want to. So, as an example, if you plug and shove, you'll find an expression for the average energy. This should be no surprise. Or for the pressure volume product, remember this is the characteristic function. PV is the characteristic function for the grand canonical partition function. So it has the particular simple form. Where, of course, we get the plus and minus. And it's you can calculate these quite readily, or and of course once they're calculated, they can be tabulated, and then you no longer have to calculate them. They're always there. So you can also look these up in tables, just as the last chapter there was a table of thermodynamic functions in terms of the partition functions. So I think that's it. Any questions?
For the pressure volume, is there a sum of logarithms? Since the grand canonical is a product of terms? Or?
Yeah, there's got to be. I must have left that out because if there's an epsilon sub I, there's got to be a sum in here. Log of the product is the sum of the logarithms, right?
Mm-hmm.
Yeah, that's got to be there. Mm-hmm. Okay.
So that's the end of chapter 4, is that it?
And this was obtained by taking a partial derivative with respect to beta, right? That's how you got the energy. So yeah, I just finished chapter 4. That's all I'll say about chapter 4. So, what's the next chapter in the book? Well, it's 5, I know that, but I figured that out. I got a PhD after all. The ideal monatomic gas. So please read that over. I'll probably put some homework on my website before the next class, so you can get a start with this stuff at the same time that you begin reading chapter 5. Okay. And you know, if this is